Hello, everyone. Today, it is an honor for me to introduce our work about mechanized verification of graph manipulating programs. I'm Shengyi Wang, a new graduate PhD from NUS. This is a joint work with Qingshan Cao, Anshuman Mohan, and Aquinas Hover. We focus on verifying graph manipulating programs written in real C code with end-to-end machine-checked correctness proofs. There are several obstacles about this task. First, graph programs are hard to reason about, but they are widely used in many critical areas. Second, the C programming language is hard. It contains many subtle semantics in some places. For an end-to-end machine-checked proof, we must handle all subtle semantics properly. The last obstacle comes from the machine-checked proofs themselves. They are merciless and lengthy. This is our strategy. We adopt two core libraries. One is Concert, a certified C compiler which provides formal semantics of the C programming language. The other is Verified Software Toolchain, VST for short, which provides a program logic to reason about C programs based on the semantics provided by Concert. With the help of the two core library, we can certify C code against strong specifications expressed with mathematical graphs. As we can see, both Concert and VST are very large libraries. They cost more than 50 person-years development effort. So it is desirous to reuse the proof script rather than reinventing the wheels. So we made no changes to Concert. We add minimum changes to VST, only 1%. Our work uses vanilla separation logic, although we also use magic wand and quantifiers in some places. The major contribution is that our framework is general and powerful enough to verify various real C code. This is our workflow. In the left lower corner, it is a C program. It can be parsed and simplified into a Coq file, which is basically the AST of the C code. It can be decomposed into several C commands or statements. The Coq file would be further compiled into assembly code. The certified Concert compiler ensures the semantics of the C source code would be preserved to the assembly code. The green part is our major contribution. For a function, given the precondition P0 and the post-condition Pn, we verify it by verifying each whole triple of the commands. We can see the whole triples are interlocked. So they interlock together to finish the whole verification. During the verification, our mathematical graph library provides necessary concepts and theorems about graph theory used in the specification. Our spatial graph library provides spatial representation of the mathematical graph in memory and the theorems to read about them. The whole triple mechanism and the program logic are provided by verified software toolchain, as mentioned before. This is our result. We verified 6 graph algorithms, including graph visiting, graph recrimination, graph copy, 2 versions of unified, and 1 big flagship example, a garbage collector for 30 Coq project. It is a generational OCaml-style garbage collector for a purely functional language. It contains about 400 lines of C code. During the verification, we find 2 places where C is too weak to define an OCaml-style garbage collector. Here, too weak means the program contains statement which which is undefined behavior under standard C semantics. Here is the statistics of our development. As we can see, the major part is the mathematical graph library. It cost more than 12,000 lines of work. And the spatial graph library takes more than 600 lines of proof script. These lines including definition and theorems. 5 examples, excluding garbage collector, occupies 3,000 lines of code. The garbage collector is a large project, which is even bigger than the mathematical graph library, more than 14,000 lines of code. The total development contains 43,000 lines. Now let's take an example to illustrate our method, the unified algorithm. The problem is classic. Given a bunch of elements which belong to different sets, disjoint sets. Now, given any two of the elements, can we judge whether they belong to the same set or not? If they belong to the same set, how to join the sets efficiently? Computer scientists invented very sophisticated data structure and algorithm about this. As we can see, the major function in the unified algorithm is the find. The elements are encoded as a structured node. Each node represents one element. The node contains a pointer parent to other nodes. The right side of the slides represent one set because they finally point to a single special node. Given a node, the find function will trace its parent recursively until it finds the special node, which here we call it the root because it points to itself. Then, before returning the result, the find function will redirect all passing nodes to the finding roots and then return the root. Now, how to specify the behavior of this program and how to prove it? We treat it as a graph. Given a mathematical graph and its memory representation graph rep, given a valid vertex x of the gamma. After the execution of find, we get a gamma prime, another graph, which is equivalent to gamma in some sense. And the return value is the root of x in gamma prime. Now, the problems are how to define gamma, the mathematical graph, how to define the predicates graph rep gamma, the spatial representation of the graph in memory, how to define other predicates, such as the graphical equivalence and the root of x. Finally, how to prove this specification. We will answer these questions in the following slides. First, how to define graph. In mathematical textbook, graph is just vertices, edges, but in our formalization, we define graph like this. V is the type of the vertices. E is the type of edges. Source and the destination function take edge as an argument and return the source and the destination for the edge. Sometimes it is useful to represent partial graphs. So we add validity predicates to edges and vertices. V valid, E valid are the validity function, a validity predicate. This pre-graph just barely gives the shape of the graph. Sometimes the label attached to vertices or edges are useful. So we define labeled graph. Based on pre-graph, it adds 3 more functions. VLabel for labels in vertices, ELabel for label in edges, and GLabel for label in the whole graph. LV, LE, LG are types for the labels respectively. Even though it is not enough. In our example, the unified graph is very special. Every node in the graph contains only one outer edge. This property, we encode it into the soundness condition of the graph. So we finally define our graph as a general graph here. With the definition of graphs, we can define other graph theory concepts, such as paths, which is defined as the starting vertex V0 and the linking edges. Then, based on the definition of path, we can define reachability. This reads, T is reachable from S through path P in graph gamma. The definition is here. The predicate valid path is quite intuitive. It just says the path P must be valid, which means V0 must be the source of E0, and all these edges are linked, which means the destination of E0 is the source of E1, and so on. Sometimes we don't care about the concrete path, so we put existential quantifier here. This reads, T is reachable from S in gamma. With these definitions, we define more definitions and prove more theorems about them. They together form the mathematical graph library. Now let's go to the spatial representation of graphs. As we can see, graph is represented by a set of nodes. And the node in memory is just a two-field struct pointing to each other. The second field is a pointer. So it is natural to use separating conjunction to link them together. So this graph rep is just a bunch of vertex rep representation. The big star here is the iterated separating conjunction, the chain of iteration, the chain of the separation conjunction. And the vertex representation of the V in gamma is here. V points to its label, and the offset points to its parent. And the parent function is defined by the functions in mathematical graph library. Destination, the only one outer edge, and so on. To reason complex objects like graphs, we need special spatial inference rules. Hober and Veled propose the RAMIFY rule, which can be explained here. We want to prove the Hall triple G1, C, G2. But what we have only is the local effect, L1, C, L2. From the frame rule of separation logic, we can attach arbitrary frame here to make this holds automatically. And to get the final Hall triple, we need the G1 implies L1 star F, and L2 star F implies G2, which means we need to choose a proper F to make these two happen. Luckily, we have this in general. So we can choose F as L2 star G2 to make the right side codes automatically. Now, we only need to prove the left side. G1 implies L1 star L2 the G2. This part, left part, we call it the RAMIFY application. This rule, called the RAMIFY rule. In our concrete application, we find this is not enough because the side condition is very restrictive. We generalize the RAMIFY rule to a localized rule, which relaxes the side condition here. We introduce an intermediate assertion R here. And we also allow existential quantifier in the post condition. It is proved in our work. Now we have all necessary components for the specification we'll find. Here is a concrete definition. Graph representation of gamma is just here, as mentioned before. The root of the x is defined here by reachability. The return is reachable from x in gamma, and the return cannot go anywhere but itself. If it's reachable to y must be return itself. The UF equivalent of gamma 1 and gamma 2 is defined by root. If x has root R1 in gamma 1 and R2 in gamma 2, then R1 and R2 must be the same, which means although the shape of the graph gamma 1 and gamma 2 are different, but any roots are not changed. Now we can prove the key execution path of the find function. Given the precondition, the post condition, the first one is easy. We just get a P points to its parent. Second is a recursive call, which we can reuse the specification from gamma to get a gamma 1, which is equivalent, and find the root P0. The third one is tricky. Of course, we can say from gamma 1, by this change, we get gamma 2, which is the redirection of the parent. But prove it directly is not obvious. While prove this local effect are obvious. Parent becomes to P0. Now we have global rule or global objects. We have local rule. We can use our localized rule here. After that, we just need to prove the RAMIFY application. But this one does not mean imply the end directly. We need to prove the gamma 2 is the gamma prime we want, which means we need to prove it's equivalent, and the P0 is the root of gamma 2. Then we'll finish the proof. This means it leaves two proof obligations. One is the RAMIFY rule, RAMIFY obligation. The second one is a mathematical inference. This spatial inference can be solved with the help of our spatial graph library. And this pure reasoning can be solved with the help of our mathematical graph library. In the rest of the time, I will briefly discuss the generational garbage collector. It contains 12 generations, and it's a functional. It's for functional programs, so there's no backward pointers. This garbage collector uses Chinese Mark and Kobe algorithm, which will trigger cascade of further pairwise collection once a receiving generation exceeds its full foundedness. Most tasks are handled by two key functions, forward and doScan. This is the visualization of all theorems we used to prove the garbage collector. Each stick is one theorem. And these curves are the dependency of these theorems. As we can see, it can be roughly classified into several categories. The pure mathematical property of the garbage collector graph, the spatial graph, theorem about the graph, and the proof of each function. And this one is a functional correctness proof, standalone. That's all. Thank you.